All right, everybody, welcome in. So we're getting close to the end here. We're not there yet, but we're getting close. So I'm gonna start off with. Sorry, accidentally clicked my mouse there. Um, if you're on the YouTube stream, so gonna start off with a little bit of an overview of what to expect from the next couple of weeks, because that's what we have left. 2 weeks left. So congrats if you've made it to this point. It's hard work. You're giving up your summer to do this, so good job. You're almost there. Just keep at it. You don't want to give up now. You don't want to have worked for a month and then sort of throw it away. So keep at it. Keep doing the homework assignments. Keep trying to get those points. Get yourself ready for the test, and hopefully you'll be good to go. A lot of you are looking pretty good as far as your scores. Getting the homework done, decent on the test, passing score at least. Some of you are struggling a little bit, but that's okay, right? You can still get there. So if we look at our calendar here, what we see is, if I move that over a little bit, we are here. Today's the 18th, so we're here in this week. So chapter 4 was due yesterday, and then chapter 5 is due on Sunday, and then you kind of need to be ready to turn chapter 6 in on Tuesday, and then chapter 7's due Friday. Here's what I'm going to say. Chapter 7 is the one on, those are the additional topics. Those aren't going to be on the test. So you should do the homework assignments so that you've worked through it and understand the material. But I'm not going to put chapter 7 on the test, mainly because you haven't really had enough time to get comfortable with it. I mean, at that point, you'll have learned it 1 or 2 days ahead of time because we move so fast in the summertime. You'll have learned it 1 or 2 days later. You're being tested on it. That's pretty brutal. So you will be responsible for doing the chapter 7 homework. That will be part of your grade, but the exam will not include chapter 7. Be aware the due dates at the end of this that are coming up for the end of the class cannot be extended, right? Because I have to turn in grades for the course. So it might seem like, oh, well, can't you give me another day or two or whatever to work on the homework? The answer is no, because as soon as the class ends, I have pressure on me to get grades in immediately. So that's part of my responsibility as the teacher. And many of the things that you all want, like you want to show your transfer for, to the university that you're going to and stuff like that, those can't happen until grades are submitted. And then it takes a little while to work their way through the system, whether it's going to financial aid or it's going to your transcripts or it's a prerequisite. All that kind of stuff has to happen. So please be very aware of the due dates as we approach the end of the course. They cannot be extended. There's no time because the course is going to end. So be aware. I will, as of Wednesday, I'm going to put up a practice exam on Wednesday. So you can start to prepare for that final. That gives you, depending on when you have your appointment set, that gives you at least a few days, some of you a week or maybe even more to get that test, to work on the practice test so that you can do well on the exam. But make sure you're getting those homework assignments done, right? Make sure you're getting those things completed so that you can get those points. Those points are going to be important. Let's see, there's a question here. Problem 7 from 5.1. Okay, so I have a request for a problem to look at, and that may be part of what we covered today, so I'll take a look at that in a minute. One thing I did want to point out, I had a few questions about 4.4. Students were having issues, and I admit the problem is not laid out very well. Like it wasn't even obvious to me exactly how they wanted the answer. I had to play with it for a couple minutes till I figured out what it was they were looking for. So I just want to show any of you who are still working on this or want to go back and get your points. I think it was problem like 17. Yeah, it's this one. So question 17 on 4.4. The way they want you to write the scientific notation, let me make this bigger. I know it's super confusing because it looks like it's not letting me scroll. Let's try this. There we go. So see how they're writing their scientific notation and it looks like an X right there. I know some students were trying to use an X because, that kind of looks like an X. But this is actually the times symbol. It's what you probably learned back in like the 3rd grade when you started doing multiplication. They teach you that X, that cross, is the times symbol. It's not exactly an X. It's a little straighter. But it wasn't clear because if you use that drop down, you don't see that symbol anywhere, right? You're not seeing that times symbol. I think that's maybe an oversight on their part, right? But the key is what you want to recognize is you can use the basically Shift 8, so that star button. So if you look at the 8 on your keyboard and hit Shift, it's like a little asterisk. Well, when you put it in here, it makes it like the other multiplication symbol. Although that's not clear because this is a dot and they're showing you to use that thing that looks like an X. So it's totally reasonable that some of you got confused with that. It sounds like some of you figured it out, but some of you got confused. Totally reasonable. Don't worry about it. That's how you do it. That's the symbol that you want to use. So if you weren't able to do it, go ahead and go back and try to get your points using a late pass or whatever. Okay. So that was one question that I had. Let's see if I can put this back like it was. So I think that's it from chapter 4. We're getting into chapter 5, which is kind of a bigger chapter. There's just a lot going on. There's good videos for it. I'll cover the things that I think that you probably need to see the most, which is kind of the concepts, and then the details should be available in the videos that are posted for you. Okay. There's a question here. Yep, so that was a question I answered a minute ago. There will be a study guide for the final exam. You should see that Wednesday. The final exam is not multiple choice. It will be more traditional where everything is written out and you'll show me your work and you'll get partial credit. So even if you miss the problem, you might get like 40 or 60% of the points or something like that. So, yeah. So there's that. Then I have a question here. When the course ends, how do we go about finding our final grade? Can we message you to find out? The problem with messaging me is that actually slows me down from being able to compute grades. So what happens with final grades is I submit them to the school. So I calculate your course grade. I submit it to the school. The next day, those grades will be available to you in your school portal. So you only have to wait 1 day from when I submit them. Is how it's going to work. So I will try to get those grades done as soon as possible. And then I'll submit them, and then you'll have them. But we're actually not really even supposed to message grades. There's laws about your privacy. Like I can't even talk to other professors about your grades and stuff like that. There's state and federal laws, FERPA laws protecting that. And when we send an email or a message, we don't actually, like, that's kind of risky if you think about it, because then that message is in there. And we've had instances where, say, maybe someone from your past still has access to your email, and then they're getting in there and then they can see that private information, and the school can actually be liable about that because the reason that person got that information is because we put it in an email. So technically, we're not supposed to send emails. I know you have teachers who do, but we've been told that it's actually poor form because it could cause problems for the school if someone else, you left your email open and someone got in there and got that information from the school, then we're in trouble for letting that information be vulnerable in the first place. So yeah, we don't actually message out grades. So, but you only have to wait 1 day from when I figure out what your grade is. Within like 16 hours, they should show up in the portal and be available to you. Okay, so that's how it'll work. So check your VC portal is how that works. Any other questions? Make sure you have your test appointment set up where the testing center is seeing about 4 times as much traffic as they saw last year. And actually, that was for the regular semester. He said they haven't crunched the numbers yet, but for this summer, they're seeing numbers that are just bonkers, right? Trying to get everyone in there for their testing. Certain weeks are really light, but then all of a sudden, certain weeks, like you can imagine, the last week of the summer session is probably going to be quite busy in there. So, make sure you have your appointment set, and then make sure you can make it to that appointment, because if you miss your appointment, you might not be able to make up. You might not be able to get another appointment made. Might be tricky. So, and I have not heard anyone. I've had no requests yet for evening, like an evening setup where I have people come in and take it in the evening. So if anyone is in need of that, make sure you get a hold of me, and we can probably set something up. But if no one is requesting that, then I'm not going to set it up, right? Right. So all those things, make sure you're current. There's going to be, in the next couple days, I'm going to set up one more Canvas discussion. So basically you'll need to do that before the course, whatever the due date is that I set for it. So just be aware of that. Keep your eyes out in case a Canvas discussion pops up. And please do it on time. The Canvas discussions don't really make sense if you do them late. I know, like with the regular homework and stuff, I don't mind allowing students to do it late. But an online discussion is kind of like a real-world discussion, where if you're not there for the discussion, you kind of missed the point of the discussion, right? It's like, you go into some discussion, and then people are talking about movies, and then the conversation moves to something else, and then 10 minutes later you go, oh, well, I like Interstellar. And everyone's going to kind of look at you and go like, what? That's not even what we're doing anymore, right? It's the same thing. If you enter a discussion late, you're not really participating in the discussion when it's online, right? You're not really getting that benefit of the whole point of those discussions is to sort of have some interaction among people. But if you're just throwing a thing on late, you're not really participating in it. So that's one of the many reasons why the Canvas discussions cannot be done late. So please watch those due dates. They're usually not overwhelmingly difficult. Just make sure you go in there, get your points. Those points will end up they'll end up in your grade. So try to get those done on time as much as you can. Okay. Excuse me. Okay, I think that covers the things I wanted to say at the beginning. So that gives us about an hour to jump into the actual material. So this whole chapter is really about systems of equations and sometimes systems of inequalities, but really the big push is about systems of equations. And what is a system of equation? How do we do it? What do we do with these things? What do they mean? How are they helpful? So what I will say is systems of equations are hugely useful, very, very important. I know some of these topics, I say like exponentials are important, and they get used all over the place. But sometimes people don't really, I think, maybe believe that too much, because they're like, well, I don't see exponentials getting used. But they do get used all the time. Interest rates, different types of growth rates, they're used all over the place. Systems of equations is another one of those topics that is hugely useful, but I think people don't always realize how useful it is or how widely used it is. Someone will say like, well, I don't use systems of equations, but that's because you're probably not in a technical job yet. Some of you will be, but where you're using this kind of stuff, and it doesn't always come up in like everyday math that people need, just like going to the grocery store and stuff like that. But systems of equations gives rise to an area of math called linear algebra. Some of you will take an entire semester, sometimes multiple semesters, of linear algebra and just learning all about like this chapter. You'll expand it. Some of you will take years worth of this material. It is a hugely, like, in every business situation, every science situation, all sorts of problems can be solved using systems of equations. And that's actually happening more and more in society now that we can create massive systems of equations and be able to go through and solve problems using them. This is happening on computers every single day, all over the place. I used systems of equations in my graduate work. I had computers crunching massive, absolutely massive systems of equations, and they would crunch on it for 6 or 7 days and then come up with a solution. This stuff is used all over the place. So while the problems that we do in the course are sometimes kind of silly, that's because we're just trying to come up with some very simple problems where you can get the basics of how systems of equations work. In real life, these things are used to figure out things like traffic. Anything that has to do with a network, you're trying to manage a network, is going to be using in some way systems of equations. Basically, if you name an area of science or business or whatever, there are people in that area using systems of equations. So please just realize it's very, very important. And like I say, those of you who are going on to computer science will take tons of linear algebra, lots of systems of equations, stuff like that. So it comes up a lot. So let's dive into it. Someone had a question about a particular problem. Let's take a look. 5.1, number 7. Oh, okay. So we'll talk about this. So there was a question for 5.1, number 7, I think is what it was. Let's see. Yeah, 5.1, number 7. We'll go over that because that's part of what we're going to talk about today. So we'll go over that. So what is a system of equations? And then in a little bit, we'll get to systems of inequalities. And then, these topics are going to pop up for the chapter. But let's take a step back and remind ourselves what an equation of a line is. Because if we're talking about systems of linear equations, which is ultimately what we're starting with, systems of linear equations, then that word linear is in there. We kind of need to know about lines, right? And the good news is if you're good at graphing lines and manipulating lines, which is kind of our most basic function, then you're off to a great start. Right? If you're having trouble with that, then you're going to have to get up to speed pretty quickly. Oh, it looks like I've got the hold on. It looks like I've got the class labeled wrong. Let me change this before I forget. Need to edit this. This is not updated. So math V04 10 a.m. on the 18th. Okay. Go back to where we were. Okay, sorry, I didn't want to forget. Now, if I have it labeled wrong, it's going to confuse people. So let's remind ourselves we have a couple different ways that we can go through and graph lines. The best way is the slope-intercept. If you have your line in slope-intercept form, you look at the slope, you look at the intercept, you graph the line. So, for example, y equals 2x minus 1, you look at it and go, oh, well, 0, negative 1 is the intercept, so you would go down here and you would put a point here, and then the slope is 2 over 1, so you'd go up 2 over 1, you'd put another point, and then you put a line through it, right? So that's kind of the easiest way to graph a line. You also could plot points if you want, make an XY table, pick some X values, find the corresponding Y values, plot those points, and then you draw your line through it. So you have more than one way to graph a line, but you will be needing to graph lines in this chapter. It comes up in many different ways, so you want to make sure you're comfortable with that. But what did we just do when we graphed this line? I mean, I know how we did it. We used the slope-intercept form, but what are we looking at? What is the graph of a line? What are we even representing when I look at this thing? So you want to remember that when we graph a line, what we are looking at is a visual representation of the solutions to this equation over here. So for instance, let's take a point on this line. Let's take 1, 2. Oops, 1, 1 is what I meant. Okay, so what does that mean for an x value of 1 and a y value of 1? If I plug those in here for my x and y, I get a true statement. So if I stick 1 in here for x, I get 2 times 1, which is 2, minus 1. 2 times 1 is 1. So on the right side of the equation, we have a 1. And now when I stick in this 1 for y over here, I get a 1, that gives me 1 equals 1. So that's a true statement. So every point on this line, if we take that xy value and we plug it into this equation, it works. It gives us a true equality, right? So that's what we're looking at when we look at a line, is the points represent solutions to the equation, and this is just a visual representation of those solutions. Okay, so that's a single line. We did that kind of at the beginning of the semester, and you've seen this before. That's what happens when we graph a line. So what is a system of equations? Well, a system of equations says sometimes we have more than one equation that we want to satisfy, right? If you think about this, these are constraints. If you're running a business, you might have more than one constraint on how you spend your money, right? There's spending money that has lots of constraints, right? We usually can't go out and just spend all the money we want. There's constraints on that. So that's what those equations are giving you, is different constraints on how, say, how cost can be spent. Well, we want to accommodate all those constraints. We want to make sure we're satisfying all of the constraints that we have on the decision that we're trying to make. So instead of just having one equation, maybe we have two. There we go. Let's make it this one. Okay. So now I have two equations. I have a red line and a green line. The green line, together, these two equations make up our system of equations. It's two equations, and we want to find a way to satisfy both of these equations at the same time. So the way I was just taking xy pairs and plugging it into the red equation, and it was true, we want to find ones that also satisfy the green equation. Okay? So we want to satisfy both of these at the same time. Well, think about it this way. If all the points on the red line are points that satisfy the red equation, and all the points on the green line are values that satisfy the second equation, well then, doesn't it make sense that what we're looking for is a point that lies on both lines? And what would a point that lies on both lines be? Well, that's the point of intersection right here. So notice if we take the point 0, -1, so an x value of 0, a y value of -1, if we plug those into both of these equations, it works. It's true. So the intersection point of the lines is the solution to the system of equations. Okay? So we kind of just built up what a system of equations is and how it works and what we do with it. So we're looking for the point of intersection. Now that's really easy when we have a tool like Desmos and the values come out really easy. See how this is a really nice point, 0, -1? Well, as you may have noticed a minute ago, that's not always the case. So for instance, let's make it +1. Now all of a sudden, well, where does this point lie? Well, it's hard to tell. In this case, it still comes out not being too messy, but you can see the point that like your solutions can come out to be values that aren't real easy to identify. We could make this even worse if we wanted to do, say, this. Now all of a sudden our numbers get really kind of messy. And in this case, even what we're looking at right there, that's an approximation. Those are not the actual values. Those are roundings of the actual values. So this method of visually finding the point of intersection can be very easy when we're dealing with very simple, well-behaved problems. But in reality, in the real world, you almost never get to solve a system of equations visually because most of your systems of equations are much more complex. And in the real world, numbers don't come out as integers all the time, right? Sometimes people will say, oh, I get math as long as there's no fractions. But the reality is, in real life, math is almost always fractions or decimals or whatever, right? Very rarely do things come out as very discrete values of integers. So you have to be able to deal with those. Especially since in recent years, because we have computing power, we're able to use computers to solve most of our systems of equations. Whereas, if it's a real simple problem, it probably, like the ones we're going to start with, 2 equations and 2 variables, it takes about the same amount of time to work it out by hand as it does to have a computer do it. And in the beginning, it's really important that you understand what a system of equation is, right? Because some students might say, well, if we can have a computer do it, then why am I working it out? It's because you should never use math that you don't understand. So we make you do some problems by hand so that you actually understand what's happening. And then, yes, we go, and oftentimes, not for this, like I say, for the simple ones we're doing, it's usually faster to do it by hand than to get it into a computer. But once you start talking about 3 equations and 3 variables, 4 equations and 4 variables, most people are going to go use a computer to get the answer for that type of problem, right? And the truth is, because computers have gotten so much more powerful in recent years, and largely because of, you may have heard the term big data, we are able to collect data and solve systems of equations that were just not possible, say 30 years ago, right? So, like I say, when I was in graduate school, I was having, for my research, running systems of equations on, we had like this supercomputer that was shared by lots of people, and I would sometimes get to use part of that, throw something on there, have it crunch for a week, and come back, and it would give me my solution. And those systems of equations were sometimes thousands of equations with thousands of variables. So that's something that a human could never do by hand, because you'd make a mistake somewhere before you finished, and then you'd never be able to go back and find your mistake. So yes, we do oftentimes in the real world have computers do this number crunching for us, but like any mathematical tool, you kind of have to earn that right of having a computer do it for you by showing that you understand what's happening. Right? Like, you should never use a math tool that you don't understand. People do this with statistics all the time. People use statistics that don't actually understand statistics. Our politicians do it. The news does it all the time. And if you actually understand statistics, you just watch it and go, that person has no idea what they're even talking about. They're actually just saying things that are incorrect because they don't even understand the statistics that they're talking about. In math, we're a little more strict. You don't get away with that. You can't use math that you don't understand. It's a good way to look foolish, right? Is to use math, and someone says, well, wait, this doesn't look right. And you go, well, the computer said so, but who put the problem in the computer? Who interpreted the problem coming out of the computer? You have to be able to do all that, right? The computer can crunch some numbers, but it can't tell you what it means for your business or for your research and your stuff like that. And for that, you have to have understanding, okay? So while this is a great way to sort of conceptually understand what's going on with a system of equations, we rarely solve problems by graphing systems of equations. I'm trying to remember if there's a homework problem. These are a little different. Yeah, those are all inequalities, it looks like. And then you have a couple of like word problems at the bottom. Okay, so let's get into how do you actually solve a systems of equations. And basically, I've shown you the drawback of solving systems of equations graphically, and it's because it's inexact. It's nice to conceptually understand what I'm looking at, and you should keep in your mind some of these pictures because they're going to help you understand what's going on later. But we usually, when we're going to solve systems of equations, we usually do it algebraically. We have 2 algebraic methods for doing it. But it's harder to follow conceptually what we're doing. It gets sort of algorithmic, where we just start going through and finding solutions. But it's easy to lose sense of that. Well, what am I actually doing? Why am I actually doing this? So keep these kinds of pictures in your brain when you're solving a solution and you get a single solution. You go, oh, that's like when the 2 lines cross each other, I get that intersection point. That's what it is. So those 2 things together can help you understand what's going on. So we have 2 methods for solving a system of equations. The first is called substitution. The second is called elimination. Some of you may have learned what we call the second one addition. It goes by both names, actually. There's the same thing. So if you had a teacher teach you systems of equations by addition, that's the same thing as elimination. But the other one's called substitution. And you might go, well, why do we need two methods? Right? Because the truth is you can solve any system of equations using either one of the methods. You can get it using substitution. You can get it using elimination. So why do I need two? Why don't I just use one and go with that? And the answer is because there are plenty of systems of equations that will be very easy to solve with substitution and a lot trickier to solve with elimination, and vice versa, where there's ones that are very easy to solve with elimination and much trickier to solve with substitution. So that's why we have the two different methods that we have you learn. Okay, so with that said, let's open the book and take a look at some things. Oh, this is a little unusual. Usually books start with substitution. I forgot, this one goes right to elimination. Do we just do substitution in the second one? Nope. So they kind of don't go into substitution much in the book. So I'll cover it. And there is, of course, videos in here. So I won't spend too much time on this because I've got good videos here. Where is it? Chapter 5, Systems of Equations. Oops, I've been logged out too long. So you can see I've got systems of linear equations. I'm going through showing you how to do the different methods. So there's a bunch of videos right there showing you how to do those basic ones. And then I talk about matrices here. So when we get to the part about matrices, you've got some videos for those as well, as long as a chemistry tutor video to help with that. Let's see. Yep, and then some descriptions here. Determinants in Cramer's rule, yeah. And then just trying to remember exactly which videos I posted here. Nonlinear systems of equations, and so on. And systems of inequalities. So we'll be doing a little bit of this later, but notice I've got a video in here that I made showing the systems of linear inequalities right here, and really like breaking down how that works. So remember, you're not going to get every detail that you need from our discussion in class. You're going to have to fill it in later with stuff. So let's go. Where'd the book go? Okay, so they start off by saying here we have a system of linear equations. So that just means we have, like I've mentioned, two equations, and we call them a system. Your system could have 3 equations, 4 equations, 5 equations. It could have thousands of equations, right, depending on the system that you're dealing with. This is just one example of what those things can be. So the A, B, C, D, E, and F are just coefficients, right, and the E and F are just constants. So we have what's called the elimination method. So there's 2 methods, substitution and elimination. There's videos showing you how to do those basic methods, right, inside of Canvas. But let's talk about what they mean. So a lot of times you want to write each equation in this form, ax plus by equals c. If you're using the elimination method, that's what you want. You want it in this form, ax plus by equals c. You don't want like your x's and y's on the different side of the equal sign. You know, we want this to be organized to make this problem go as smoothly as possible. So we put the x and y on one side in the, the obvious order. You kind of think about alphabetical order. So when you get to the problems where there's an x, y, and a z, you put them on the left side, and then you're going to put x's first, then your y, then your z, and you're going to go from there. Okay, so that's all that's talking about. Step 2 is eliminate x from the second equation by by adding a suitable multiple to each equation. You actually can choose whether you want to eliminate the x or the y. So right here, they're telling you specifically to eliminate the x, but you get to choose. You could eliminate the x in the first equation. You could eliminate the x in the second equation. You could eliminate the y in the first equation. You could eliminate the y in the second equation. It doesn't matter where you start. You're going to end up with the same solution no matter what. So basically, you pick a problem or you pick a variable and then you try to eliminate it. Now, the good news is so at that point, you've solved for one variable. Once you've solved for one variable, you just go back to your system, plug that value in, and you can solve for the other variable, right? I know this probably doesn't make a lot of sense yet, but I'll give you an example in just a second. So let's look at this one. So we've got, let me make this a little bigger here. We've got x plus y equals 30 and 3x plus 8y equals 180. So here's a system of equations. It's already written in the form where the variables are on the left, the constants on the right, and notice how we're consistent with our variables. The x's are first, then the y's come second. That's what we're supposed to do to set the problem up. And in fact, that was part of the question here in 5.1. Someone had a question about number 7. Notice at the beginning of the problem, it says write the system of equations in this form and then solve. So all they're saying is what I was just talking about. You get all your variables on the left, you put your x's first, your y's next, and then you've got the constants over here by themselves. And then you're going to solve that system of equations using elimination or substitution, whichever method you want to go through and do that for. Okay. But at least that's the directions for number 7, is put it in this right form and then go through and simplify everything. This one has some fractions in it, so we'll talk about that in a minute as far as what you actually do to take care of that part of things. Oops, where am I? Here's where I am. Okay, so we've got our equation, so we've got it written in this form. So now what we want to do is get rid of one of the variables. We want one of these variables to cancel. So what you want to do is get the variables to have the same coefficient on them, but with the opposite sign. Okay, so you could either get rid of an x or you could get rid of a y. Since the numbers are smaller on the x's, it's probably easier to go with the x's. Okay, so we've got x and then a 3x. So what I want then is this coefficient on my x in the first equation to be a -3, because it has to cancel out with this 3 down here. So -3x plus 3x equals 0. That means those variables cancel out, right? So that's how I know to multiply the first whole equation by -3, because it's going to make my x's go away. So that's what they've done here. They multiply by -3 to the first equation to get, which will be -3x. Oops, let me scroll up. It'll be -3x minus 3y equals -90. That's what you get from the first equation when you multiply the whole thing by -3. Okay, so just to be clear, we picked -3 because I want it to cancel with this +3 down here. So when we do that, when we take the -3x minus 3y equals -90 and I add to it the original second equation, 3x plus 8y equals 80, notice how we can just add in columns because we were very careful about where we were writing things and making sure the variables are on the left, they're all written in consistent columns. That makes this addition part very easy. And in math, easy usually means less mistakes, right? We want to make less mistakes, not more. So the -3x and the +3x cancel. That was the whole point of all our work. So they cancel out. -3y plus 8y gives me 5y. And then -90 plus 180 gives me 90. So we end up with the equation 5y equals 90. Now, this is good news because we took equations that had 2 variables in them, and we turned it into an equation that has 1 variable in it. That's better, right? Because this equation right here, we can solve this easily. I'm just going to divide both sides by 5 and get, what, 18? Yep, so we end up with y equals 18. And this makes it, at this point, it's easy because now that we know y equals 18, you just go back to one of your original equations, whichever one looks the easiest to deal with, usually the one that has the smallest numbers in it. In this case, it was that first equation, x plus y equals 30, right? That's one of our original equations, right? X plus y equals 30. Well, now what we do is we basically take that y equals 18 and we substitute it in here to get x plus 18 equals 30. So that's what they're doing. X plus 18 equals 30, so x equals 12. So we know that x equals 12 and y equals 18 is a solution to that system of equations. Now, here's one nice thing about system of equations. It took us some work to get through that answer, right? But checking systems of equations is very easy. If you know the solution or you think you know the solution, checking if that solution is correct or incorrect is very easy. All you have to do is go back and plug back into both original equations. So we had what? X is 12 and y is 18. So let's come back here. So that would be 12 plus 18 equals 30. Yes, that's true. And what down here, we would get much larger numbers. Let's see. This would be 36 plus, I don't know what 18 times 8 would be. But if you plug it in, it's going to make this second equation true as well. So when you get to the end, your x and y pair, you should plug them into the original equations, both of them, and make sure that they work. Some people just trust that their work is good. And that's a big mistake because it's very easy to make a mistake when you're doing these systems of equations. And just trusting that you didn't mess up is a good way to get the problem wrong. When it only takes a few seconds to check the work, you might as well just check it, right? Sometimes people get kind of lazy and just plug it into one of the equations and go, well, if it works in one, it probably works in both, right? Not necessarily. It depends where you made your error. If you made your error in the place where most of the problems occur, then it's going to fit one of the equations and not the other. So that's why you know, on a test or something important, you really want to make sure you check all the equations to make sure that your solution fits into all of them. Okay? Students give themselves sometimes a false sense of security by checking the first one and then going, oh, well, it works there, so it probably works in the other one. Not necessarily true. Depends where your mistake was made. Okay? So that's the basics of the elimination method. Like I say, remember, I have videos on both elimination and substitution inside of Canvas. So watch those and you'll get the basic procedure for solving the systems of equations. Okay, this shows us, this is another one of those graphical representations. This shows us the three possibilities when you solve a system of equations that has two equations in two variables. So your system of equation can have, you know, as long as the numbers are bigger than 2, it can have 2 or more equations and it can have 2 or more variables. And they don't always have to match. A lot of times they do. Like you'll do a lot of problems that have 2 equations and 2 variables. But you could have a problem that has 3 equations and 2 variables, or 12 equations in 8 variables, right? There's lots of different ways that these things can occur. We're very restricted when we talk about this simplest case, which is where we start to learn about systems of equations, which is where we have 2 variables and 2 equations, okay? Because that's just lines in the plane, right? You'll have some homework where you do 3 equations and 3 variables. That's now 3-dimensional space. So that's where you have planes in a 3-dimensional space, right? But we're just dealing with the 2-dimensional case right now where we have lines that are inside of a 2-dimensional space, a plane basically, right? So this is the situation that happens the most. This should look kind of familiar. That's what we looked at a little while ago. Our 2 lines from our system of equations have an intersection point, and that intersection point is the single solution to the entire system. There's exactly one point that fits both of the equations. This is what you're going to run across most of the time when you're doing this chapter. Okay, this is usually going to be the outcome. We call that a unique solution with an independent system. Unique in mathematics means there's only one of it. excuse me, means there's only one of it. Okay, and independent means that your equations are not based on each other. We'll go into in a few minutes what that means. Okay, but you can also have this possibility. What if you had parallel lines? Well, remember we talked about how the solution to a system of equations is the point of intersection. Well, what happens if you have two parallel lines then? Well, two parallel lines will necessarily have no intersection. Therefore, there will be no solution. If the solutions are the intersections, then if you have no intersections, you have no solutions. So this is a possible outcome, is that your two lines are parallel, leading to a no solution type situation. Okay. We call this an inconsistent system because it's inconsistent. There's no possible working outcome. There's no solution. Okay. This third one might look kind of silly because you go, wait, there's only one line. Where's the system? Well, that's how the third one works, is that both lines in your system are actually the same line. And that might seem silly. Why would we have two equations that are the same line? Why wouldn't I just deal with the one line rather than the system of equations? Well, this can happen for a couple reasons, and it usually happens by accident, right? Remember how I talked about how the equations are constraints? Well, maybe in your business or your research, you have two different areas where you're being constrained, and you don't yet recognize that they're actually the result of the same thing. Well, you would put those constraints into your system, not realizing that you've just recreated the same equation two times, because they might not look the same, right? One might be solved in y equals mx plus b form, and the other might be solved in like intercept form, where it's like ax plus by equals c. So when you look at the two equations, you'd go, oh, those are different equations. But then it turns out they're actually the same equation if you put them in the same form. So what happens then when you go to graph those two lines is one line fits exactly on top of the other one because they're the same line, right? So if we draw one line and then on top of it we draw another line, what are the points of intersection? All the points are points of intersection, right? So in fact, there is an infinite number of solutions. Now, they're going to have you answer that on the homework where you're going to say there's infinitely many solutions. We call this a dependent system. If one of your equations can be derived, can be brought about algebraically from the other equations, we call that a dependent system, okay? Basically, it's the two graphs. So those are your three outcomes. Most of the time, you're going to get one single unique solution. That's what's going to happen the majority of the time you do these problems. You occasionally will get two parallel lines, and sometimes you're going to get two lines that are actually the same line. Those are your three outcomes. So these pictures are really helpful when you're doing this because it's helpful to be able to, like, when you're working on a problem, you go, wait, I'm confused, and you think back to these pictures and go, oh, that's the second one. I'm dealing with the second one right here. And you go, hey, that's right. It makes sense that it's no solution. Hopefully you don't have to memorize this. Hopefully you can just understand. Like, hopefully you understand why this first one has one exact solution. Hopefully you understand why the second one has no solution because there's no intersection points, right? What about over here? Why does this have infinitely many solutions? Because every point is a point of intersection. So if you can understand that basic logic, you don't have to memorize it. You can just think your way through it each time. Okay, so I just want to show you what this looks like. This is great that we can visually understand what's happening with our graphs when we get these three different types of solutions, right? But as I mentioned, we usually solve things algebraically, not graphically. So how am I supposed to identify which of these three situations I'm dealing with when I'm not going to graph the things that in the first place? What do I do? And the answer is we just learn what the solutions will look like algebraically. So that basically they're taking, here's a problem. This is example 2A in the book. So they've got a system of equations. Everything looks fine. We don't notice anything weird about these equations or anything because usually you don't spot it right away. They go through, they do the elimination method. You can see they set it up so that our x's are going to cancel. We're left with some equation just in y. We're going to solve that. and we end up with our the solution x equals 2, y equals 1/2. So that obviously is the first scenario. We got one solution. The solution is x equals 2, y equals 1/2. Okay, those two values together give you one solution. Sometimes people quit when they find the first variable, but remember, the solution is the point of intersection. So the point of intersection requires an x value and a y value. So you have to have an x and a y to get a single solution. So that is what you're usually going to run across. That's the first one. People are usually good with that one because it's pretty obvious. We just got a solution, therefore that must be the solution, right? What about number 2? So we're going to look at part B here. Let's solve this one. So nothing weird looking, right? I see some different numbers in there, but everything looks fine. Well, when we go to solve it using that elimination method, look what happens. Look what happens. They set this up to have the x's cancel, but look what also happened. The y's cancel. So that's generally how you're going to know that you're in one of these weird situations, the type 2 and the type 3, the second ones we looked at right here. The first clue that you're in one of these scenarios right here where you have parallel lines or lines on top of each other, so no solution or infinitely many solutions, the first clue is that all of your variables cancel out. Not just one of them, all of them. Like when we did this problem up here a moment ago, our goal was to get just the x's to cancel, but notice how we still had some y's. When we are down here, when we cancel the x's out, notice we lose our y's as well. The y's are gone as well, and we're left with, in this case, 0 equals 0. Now, it won't always say 0 equals 0, but what you will get is an equation where all your variables are gone, and what you're left with is true. So notice how this is a true statement, 0 equals 0. So 0 equals 0 is true. 0 is, in fact, equal to 0. And all our variables are gone, and that's where I go, oh, wait a minute. So it turns out this equation was actually just another version of the first equation. And you can start to see it now that you know. You can go, oh, if I moved this around and I divided by 2, I would get the top equation. You can start to see it's the same one. So really, there's only this first equation. So we would express that in that form, right? All the points that lie on y equals 2x plus 4 are actually solutions to the equation. So this is where you would say there's an infinite number of solutions. So on the homework, see how they have it written here where you can choose between there's a single point and then you're going to put the point in here, or you're going to say there's no solution and you're going to click that, or you're going to say there's infinitely many solutions and you're going to click that one. So it just depends on what you think the answer is, whether you think there's a unique solution, no solution, or infinitely many. That's why it's helpful to have this picture in your head so you kind of understand what's going on. So that's the one we just saw where you get 0 equals 0. That's this one on the right. That's the third possibility. So then what does it look like when you're going to get the second possibility? Well, it's very, very similar with just one key difference. So for C, notice they do the same thing. You take what appears to be just an innocuous system of equations. We go through, we start solving it. You can see, look, the x's are going to cancel. And then, oh, same thing again, the y's cancel. So when we try to cancel the x's, the y's cancel as well. Except, do you see the difference? Before we had 0 equals 0, which is a true statement. Now we end up with all our variables gone, but we have 0 equals -2, which is a false statement, right? So how can we make 0 equals -2? You can't. 0 doesn't equal -2. So that false statement means there can be no solution. There's no values you can pick for x and y that make 0 equals -2 a true statement. That's how we know it's no solution. Okay, so that is how it looks when we do this right here, when we have parallel lines. No solution. Okay, so those are your 3 outcomes. So follow the videos in Canvas about how to solve for those, and then also on the homework. Looks like they have videos in here too that you can click and follow along. But you have to understand which of those 3 you're dealing with. I see people get Like I say, most people can get the unique solution fine, but I see people get mixed up between the second and third, the no solution and the infinite number of solutions. They'll like recognize that it's one of those, but they'll pick the wrong one. So you want to be careful about that. Make sure you're not doing that, basically. Where are we? And then this is down. So that should help you get through most of those ones that you... Oh, we talked about fractions earlier, like for number 7. So you can see fractions coming up in problem 5. You can see fractions coming up here in 6 and 7. So what do you do when you have fractions in your system of equations? What are you supposed to do about that? Well, sometimes your solution is going to have fractions in it. So sometimes you're just going to have to deal with fractions at least a little bit. Sometimes you can get rid of those fractions that are in the problem, and then you don't have to deal with them at all. So the whole key to getting rid of these is you take the entire equation and you multiply by the least common denominator. If you multiply the equation by the least common denominator, it's going to totally cancel out the denominators, and then you don't have fractions anymore. You're going to have bigger numbers that you have to deal with, but that's the price that you pay for not having to deal with denominators, which means not having to deal with fractions, right? So let's take a look. Oh, then they go to inequalities. So let's see. So there's a question here. How do we put the equation in that form? In which form? The ax plus by equals c form? Is that what you mean? The form that the form they're telling us to put this in at the beginning of the section? This form? Yeah. Okay. Great question. So let's do that. Let's go through a problem where we do that. So if we've got, say, negative 2y equals 7 minus 3x. Okay, so here I have an equation, and it's not in that right form. So the question, if you can't see, that's being asked in the chat in Zoom is about how do we put it in that ax plus by equals c form. So here we have one that's not in that form, right? We're looking for something that looks more like ax plus by equals c. So what does that ax plus by equals c form represent? Well, it means we've got all our variables on the left, right? Our variables are the x and the y. They're on the left side of the equation, and they're in the right order. We're not putting our y's in front of our x's. That just gets confusing. We choose the natural alphabetical order in order to organize our variables here. And the a is just the coefficient on our x, and the b is just the coefficient on the y, and then our c is a constant. Right? So we don't have this. We have a variable on both sides of the equation. We want them both on the left. And then we want the x first, then the y, then an equal sign, then the constant. So it looks like what I could do is add 3x to both sides of the equation. If I did that, I would get 3x minus 2y equals 7. And now I've got it in the right form. See how I've got, so I added 3x to both sides. I've got my x first, my x term first, my y term second, and then my constant over here. Notice how this negative 2 is sort of important. It's a negative 2 coefficient on our y, but we now have it in that correct form that we want to work with. Okay. Hopefully that answers the question. Okay, then the other thing that you're going to run across in 5.1 is about systems of or linear inequalities. So Desmos is helpful for this, but you want to understand what's actually happening when we do this. So let's say that we have a linear inequality. So something like 2x plus 4y is less than or equal to 12. Oh, if you're trying to do this at home on Desmos, you just put the less than symbol, and then watch when I put the equal sign right after it, it's going to make it less than equal to, which is helpful. And you can see it actually changes our graph a little bit. That boundary line changes whether I put an equal sign there or not. If I do it right now, so it's changing when I add that equal sign. The black is not great. Let's change that to, say, orange. That's a good one to use. Okay, so what's going on with this inequality? Well, the first thing you have is the boundary, this solid line here. That separates the things that are solutions from the things that are not solutions. So everything over here not shaded, these are not solutions. And everything over here that's shaded, those are solutions. So if you take any point from this shaded region and plug it into your inequality, it will work. If you take any point from over here in the unshaded region and plug it into this inequality, it will not work. One of the easiest ones is x equals 0, y equals 0, the origin. So let's just plug that in. What if I plug in x, 0 for x and 0 for y, then I get 0 plus 0 is less than or equal to 12? Yeah, that's true. That's definitely true. Okay, what if we plug in something over here? Like, say, the point 42. Right, that's a point from the non-shaded region. And if I plug in 4 for x, that gives me 8. I plug in 2 for y, that gives me 8. 8 plus 8, is that less than or equal to 12? Nah, that doesn't work. So the things over here are points, are solutions. The things over here are not solutions. What about the things that are right on the line? Well, in this case, if you pick a point that's right on the line, you're going to get perfect equality. And since this is a less than or equal to, it works. That's why we use a solid line. So what about a minute ago where I had it as a dashed line where it was a strict inequality? Well, if we plug in something on the line right here, we're going to get 12, right? But 12 is not less than 12. 12 is less than or equal to 12, but it's not less than 12. So that's why we use a dashed line when there's a strict inequality here. It's not a less than or equal to, it's just a less than. And then if I make it an or equal to, then we get the solid line. It fills it in because the line becomes part of the solution. Okay, so how do you do this when you're not having Desmos do it for you? Well, it's actually really easy. The first thing you're going to do is graph the line. So let's say we didn't know what this was going to look like already. Okay, so I'm going to do that. The first thing you do is graph the line. So just pretend this is an equal sign and it's a line. So remember we talked about that at the beginning of class. You can use the slope-intercept method, or you can create a table, just plot some points. Whatever method you're comfortable with graphing lines, you need to do that. So let's say 2x plus 4y equals 12. So there's our line. And now I have to shade one side or the other of this line. Now you go, well, I know which one it is. It's the lower half, this one over here, right? But that's because we just had Desmos figured out for us. If you don't have Desmos doing that, how do you know which side of the line you're supposed to fill in? Well, it's actually really easy. You just pick a point and make that a test point, and then you test it. Because when you take a test point, it's either going to work or it isn't, and that tells you if that side of the line is the solutions or the non-solutions. The only thing you can't do is pick a test point from the line, because we already know what happens on the line. On the line, you get equality. So you have to pick a point that's off the line. Here, an easy one. How about 0, 0? Well, when you stick in 0, 0 to this original inequality, it's true, which again confirms to us that this is the side that has the solutions. So that's the side that should be shaded. Okay, so you just pick a test point, plug your x and y into your inequality. If it works, then you shade that side of the line. If it doesn't work, you shade the opposite side of the line. So that's all there is to it. So you'll see in the homework, you'll have things where they say like, graph the solution set of the inequality x is less than or equal to -2. So you pick. So first you're going to go down here. Let's make this a little bigger. First, you're going to go down here, and it looks like we have to decide, am I drawing a solid line or am I drawing a dashed line? Well, if I look up here, this is a less than or equal to, so that means that the line itself is part of the solution. So that means I want a solid line. Okay, so I'm going to push that button, and notice it's giving me a little pencil now. And then I'm saying, okay, x less than or equal to -2. So I have to think about what kind of line is x equals -2. Is that a horizontal line or a vertical line? Hopefully you know that, and you said, oh, that's a vertical line. If you did, good job. So that's supposed to be at -2. So let's make that line right here. Okay. So here, let's undo this so I can show you. Let's clear it. Okay, so you go and you just pick where you want the first point. I'm here at -2. And then see how you can move it around. You can figure out where that next point goes. Well, I'm just going to, I want this line. That's the line x equals -2. So I'm going to click it. And then then it's asking me, do you want to shade the left or the right? I have to figure out. So let's see. If we pick a value and plug it in here and see. All right, let's see. What if I picked the origin, 0, 0? So x is 0, y is 0. If I put 0 in here for x, is 0 less than or equal to -2? No, it's not. So that means my point over here of the origin, that's not a solution. Therefore, nothing over here can be a solution. Therefore, I must need to shade this side. Notice if we take something over here, how about the point -4, 0? If I plug that in, -4 for x, oh, that does work. -4 is less than or equal to -2. So that means I'm going to shade this side. And then submit. And it says, good try, or good job, whatever. We did it correctly. Okay, so that's, I know sometimes people get confused about using the graphing component. It's really actually pretty straightforward. You pick if you want the straight line or the dashed line. You put your line there. And then it's going to have you shade one side or the other, right? There's not anything too complicated going on right there. Okay, so what about when we get to a problem like 12? Okay, so 12, now we have a system of inequalities. Oh my goodness, what are we supposed to do with that thing? So it's basically the same thing. You're going to graph both of those lines, and then you're going to figure out the region where both of them get shaded. Okay, so let's take a look at this. So let me break this one away for a minute. Let's look at, what do we have here? Where did it go? So -x plus 2y is less than or equal to 4. And -x minus y greater than or equal to -1. Now, I'm not telling you to just use Desmos to do this for you, but I'm showing you how this works. So see how we have the two inequalities written here? And we have, this is the area that's just satisfying the purple inequality and not the green one. This is the area that satisfies the green inequality and not the purple one. This up here is the region that doesn't satisfy either one of the inequalities. And this one down here satisfies both. So that's what you want to shade. So for this problem here, you would go through and graph both of those inequalities, and then it's going to have you pick which region you're going to go through and shade. So you're basically just doing the step we did a few minutes ago. You're just doing it twice. You're taking the part where the shaded is overlapping shading. That's how you're going to do that one. Okay, so if you can understand the problem from a minute ago, this is basically just doing it 2 times inside of the problem. Okay, and then that, I believe, is it for. Oh, you can have more than one of these inequalities. You can have 3, 4 sometimes. You can have a bunch. So just kind of be aware of that. And then we get down to here. In this case, they don't give you the equations. You have to set up the equations and then find out the solution. So what's the following table lists the calorie content for a typical fast food meal. So after a lunch that consists of a cheeseburger, a medium order of fries, and a medium cola, you decide to burn off 1/4 of the calories in the meal by some combination of running and walking. Okay. You know that running burns 8 calories per minute and walking burns 3 calories per minute. If you exercise for a total of 45 minutes, how many minutes should you spend on each activity? Okay, so this one's a little bit complicated. You have to figure out, you're basically figuring out, you have 1 cheeseburger, 1 order of fries, 1 medium cola. So you figure out what that total calorie content would be. It's going to be some number, right? 350 plus 470 plus 200. You're going to get some answer. And you want to burn off a quarter of those. So you'd multiply by 1/4. So take that. Oh, someone just mentioned roll. I do need to do that. Thank you for pointing that out. I'll do that in just a second. So then you would figure out what 1/4 of that value is. And then you have to figure out, so you'd have 8x, like 8 calories times per minute, and then 3 calories per minute. So you want a combination of burning 8 calories and 3 calories to figure out how you're going to get it to equal that value. So let's see. And you want it to equal 45 minutes. So basically, what value of you're going to have. It's weird how they have this labeled. This shouldn't really be your. It's a little strange how they have this problem set up. But basically, in this case, you just have to set up the system of equations, right? And then you're going to solve it. So many of the problems you've been doing so far, you solve the system of equations. Here you have to set it up. And I would work through that, but I do have to take roll, which was pointed out. But there's a video here, so they're going to help you walk through it. But I don't have time to, unfortunately, I don't have the time to go through that. So please stick around while I take roll so that you can get credit for being here. So what do we have? Oh, and Janelle's up there. Okay, I think I got everyone. I think everyone's here today. Okay, good job, everybody. We are out of time. So we'll continue with this chapter on Thursday. Is today Tuesday? It's Tuesday, Thursday. So we'll continue with this on Thursday, but you do want to be moving ahead. I kind of set the stage for a lot of the stuff. Do try to move ahead as far as you can through chapter 5. I'm not sure exactly how much we're going to be able to cover on Thursday. But try to move through that chapter. Good work, everybody. Anyone want to stick around and ask me questions in on the YouTube or on the Zoom stream? Feel free. Otherwise, thanks everybody, and we'll see you in a couple days.